Hey everybody. So for this R script file, I'm just going to show you one essential topic that you will hopefully use on your homework, and then excuse me, and then I will highlight a couple of other non-essential topics, but some things that might be useful for you in your research or your work, and maybe on the homework as well. So hopefully you've had a chance to look through the guide for the nested F-test. This will make this make a lot more sense. A lot of the guide is actually repeated here, so you can see it in multiple places. And we'll just go through how to run that in R, the example that I used in the guide. So to do the nested F-test, first I'm going to load up the NBA data and check it. Good. Everything looks okay. And what the nested F-test lets us do is compare two models, where one of the models is what we call nested in the other model. So what do I mean by that? And what does the nested F-test accomplish? Well, let's say that I have a model where I'm trying to predict the average number of games won, and I start with points per game and assists. And I can run that model and check its results and look at my different statistics and t-scores and p-values. And I can do all of that, and that's great. But let's say I wanted to evaluate another model that starts the same, but then adds in multiple other explanatory variables. In a sense, this smaller model is nested in what we would call a larger or a fuller model. If I wanted to say add steals and blocks as explanatory variables, I could check them one at a time, or I could put them both in the model at once and do a model comparison. So what the F-test lets us do, the nested F-test, lets us compare two models where one is a subset of the other one. So what this nested F-test is doing is saying a few things. One, it's starting off by saying, my null hypothesis for this nested F-test is essentially that both steals and blocks are not significant, that they have slope coefficients that are equal to 0. Again, we're saying that the things we're adding in, the null hypothesis is that their slope coefficients are equal to 0, that they don't add any additional explanation. The other way to interpret the nested F-test is to say that this fuller model, this bigger model, is what we're doing is testing whether or not this bigger model adds significant explanation of the response variable above and beyond this smaller model. So the smaller model does some explaining. Well, and the bigger model also does some explaining. So we want to compare, well, does this bigger model explain significantly more variation than this smaller model? And instead of just looking one variable at a time, which you can do, sometimes you want to just test a whole bunch of things. Maybe you want to test 3 or 4 or 5 variables that are different between these two, that are added on to the simpler model. So a nested F-test is nice because it lets us do that. It lets us test what we might call a subset of predictors all at once. And just to sort of drive this point home, I ran this reduced model, and I looked at it. And I can also run this full model, which adds 2 more explanatory variables. And I could independently look at that. And now, I can tell just looking at this example that steals and blocks, they're both statistically insignificant. The adjusted R squared does not add much, 0.05798, 0.5915, excuse me. And then like the F statistic here is 21, here it's 11.5, so the F actually goes down. In this case, I could just look at these 2 models and without even doing anything formal and just say, yeah, these extra 2 variables of steals and blocks, that's not, they're not helping. This is not a better model. But this is a really obvious case, and it will not be obvious every time. So let's just pretend that it wasn't so clear that this fuller model was worse as it is in this case. Let's just pretend that, well, it looks like maybe it's doing something. Let's just pretend that. Then how do I compare adding in these 2 additional explanatory variables above and beyond this simpler model? So to do this, to do the nested F-test, I just simply run the ANOVA command. And we will work more with this once we get to ANOVA. But it's actually really useful right now because it lets us do this model comparison. It lets us do this nested F-test. And the way this works, you simply put in your 2 models into your ANOVA command. And I will say this, it does not matter in which order you put these in. So I could do it this way, or I could do it this way. But it just reads them differently, and the conclusion is the same, but the table looks a little bit different. So just so you're aware, you can put it in any order, but I'm going to recommend that you put in the smaller model first, and you'll see why in a second. So just put in your simpler model first, your bigger model second, and I'm going to do Control-Enter and run that. And let's see what we get. So the reason this is nice is that, and why you do the simpler model first, it reads it in a very intuitive order. So it says, great, I'm going to start with the simple model, and then I'm going to add on the more complicated, the fuller model, and then I'm going to test the difference in basically the explanation that these 2 models do. And there are some things down here that we'll check later on when we do ANOVA. But in terms of making a conclusion, you can skip right to this F score and this p-value. So what this means, this p-value of 0.2685, that is non-significant. What that means is that my fuller model, this addition of these 2 explanatory variables, does not add significant explanation of the average number of games won above and beyond my simpler model. So a non-significant, a high p-value, means that my original simpler model is best. Purely from a statistics standpoint, not obviously from a theory standpoint. That's different. And really, that's it. So if this was statistically significant, say 0.001, then we would know, oh, the bigger model actually does add more significant explanation above and beyond the simpler model. And just to demystify some of the parts of this, what this is showing us, the first column is saying, what's my error degrees of freedom? So it's the degrees of freedom you would use on the t-test. That's what this is, 27 for the first model, 25 for the second model. And then it's giving us our residual sums of squares, or as we've been calling it, our sums of squares error. RSS, in this case, is just the SSE, the sums of squares error for each of these models. This little number down here, the 2, is simply how many additional predictors I am testing that's different between these two models. And then this column, the sums of squares, this is the amount of additional variation that is explained by my Fuller model, by my additional 2 variables. And then finally, the F and the p-value to determine things. So I'm not going to have you interpret any of these things in the F-test table, but if you do a nested F-test on your homework 2, you don't have to, but it could be very helpful, then all you need to do is run this and then check the F statistic and the p-value to see whether or not a bigger model that you're testing does significantly better above and beyond a simpler model. And that's it. One last important point about this, you have to have the simpler model completely contained within the fuller model. In other words, I couldn't have a smaller model with its own unique extra variable like turnovers. That's because then suddenly we're not just comparing nested models anymore. We're comparing something different. And that's a separate topic and a separate discussion. But for the purposes of doing this test in this class and doing the nested F-test, have your simpler model be completely contained in this fuller model. Great, so that's the essential topic. Let me just, in my last couple minutes here, let me just briefly touch on these other things. So I have a few things. Let me quickly show you this. I've had you do scatter plots. Do not do a scatter plot matrix in this course or for your homework 2. But if you're just curious, you want to do a scatter plot matrix between an explanatory variable, between basically any sets of variables, you just use the pairs command. And if you want to see a scatter plot between any sets of variables, all possible combinations, you just simply put them in the pairs command. So if I want to see a scatter plot between field goal percentage and then rebounds, assists, steals, turnovers, blah, 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 and scatter plots between total rebounds, assists, steals, turnovers, points per game, da, 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 I just simply put them all in my model and I tell it which data I want to run. And it gives me this nice scatter plot matrix. Again, don't do this for the homework. This is difficult. It can be difficult to interpret, but this might be useful for you in other things. So here's a scatter plot matrix. These 2 things down here, I'm never going to have you use these, but in case it comes up, I just want you to see what they are, and here's where they are. So leverage is just a way to describe how much influence an individual data point has on your regression line. So it's a very particular measure of influence, you could say. So you can get these leverage values and you can check for whether or not they significantly impact your line, your regression line, that sort of thing. So I'll let you read through that. I'm not going to do anything with it, so I'm not going to spend more time on it. And then Cook's distance takes into account both leverage and the size of the residual. So remember, the residual is the distance between our model and our data, and that can have an impact on our line and our conclusions. So we can do this thing called Cook's distance to capture the effect of the residual and the effect of the leverage. And it gives us a measure of influence. But You can read through that. I'm not going to have you go through it. I just wanted to point it out. And I'll quickly talk about correlation in the next video.